Alright, so here we begin my quick run through of the solution to mission 3. Let me zoom in a bit. I'm not sure I have too much to say here. I'm just going to walk through my solutions. As you can see, these are the problems that were assigned. And so here we go. So the first one, it's not too bad. Is this, here's a map, and where is it a local diffeomorphism? So in other words, where is the differential 1 to 1 and onto? So since this is a mapping from R3 to R3, it suffices to find the places where the Jacobian matrix of the map is invertible. And so I do that. Here's the Jacobian matrix, and the determinant of that is what it is. And so it looks to me like as long as you're away from the points where, as long as you're not on the plane, x plus y plus z equal to 0, you should be okay. It's a local diffeomorphism away from the plane, x plus y plus z equals to 0. Now, I'm not saying that it's, well, I guess I am saying it's not a local diffeomorphism at those points. That is actually true, because the differential would not be an isomorphism. So it's not a local diffeomorphism at those points. All right, which is not to say, of course, the more subtle thing, which is, does the function actually have a local inverse at the points on the plane? Like that, I don't know. Maybe, maybe not, but we don't have to say. So going on. Here we have a question about smooth manifolds, M, N, and P, and some conditions that you have. Mapping G from P to M, continuous, G smooth if and only if, the composite of F and G smooth, and then here F surjective. Notice they've changed the definition of G. This is not the same G. G from N to P is any map, then G smooth if and only if the composite of G with F is smooth. And so both of these problems basically, for me, boil just down to sorting through some like pictures. And so to prove that, all right, so I'm going to assume G is smooth for part A, right? To show F composed of G is smooth is to show that the local coordinate representatives are smooth. At least that's the, if I'm not going to use a theorem, that's from the definition, right? So I'm a little bit fuzzy here in my solution technique. My apologies, but I'll let you guys get away with the same, I suppose. So here, phi P and phi N, there'll be charts defined near P and near Q as pictured. Then it might be necessary to shrink the domain of phi N such that there exists a chart phi M at the chart G at G of P and M for which the local coordinate representative of F is smooth. All right, now I can do that because F is a local diffeomorphism. So not only is F hat smooth, it has an invertible local coordinate representative if I shrink the chart domain sufficiently small. And but since G is continuous, I also know that the inverse image of the domain of that is open and in P, and so we can shrink a chart domain in P to coincide with the inverse image of that. And with these restrictions in mind, if we calculate the local coordinate representative of the composite, all right, if we calculate the local coordinate representative of the composite down here, well, that's this, but I can insert the inverse in the coordinate chart there, and that's a good move because then that gives me that this is smooth and that's smooth by assumption. And if we have the composite of smooth maps on Euclidean space, then the composite of smooth maps on Euclidean space is again smooth, basically because the chain rule, but well, I don't know what's the chain rule, but it is nevertheless a theorem of advanced calculus that the composition of smooth maps is smooth. So anyway, there we have the local coordinate representative of the composite of F and G is smooth, therefore F composed of G is smooth as P was arbitrary. Now, the argument for part B is very similar. Actually, okay, I'm not even to part B. I'm still in the converse now. So now I'm assuming that, well, anyway, I'm just going to let you guys read this. Basically, the argument is you probably could make it a bidirectional argument if you did it right, but now I'm assuming F composed with G is smooth, and I'm trying to show G is smooth. So basically the game I play here is to look at the local coordinate representative of G and try to rewrite it in terms of the, I can, you notice by this calculation that the local coordinate representative of the composite is the composite of the local coordinate representatives with the suitable restrictions being made in place. But the thing is, since F is a local diffeomorphism, F hat is invertible, and as such I can solve for G hat, and I get F hat inverse composed with the local coordinate representative of the composite of F and G, but again, the composite of smooth maps is smooth, therefore G's local coordinate representative is smooth, which means G is smooth. And again, I'm using continuity of G to allow us to shrink the domain to work in concert with the other domain, which in turn must be made small enough to use the local diffeomorphism property. All right, so like there are, if you made all that explicit, I'm sure I could write another 3 pages. So part B, again, very similar kind of logic. I just try to set things out here. I'm assuming to start with that G is smooth and that F is surjective. Since F is surjective, I don't want that there. Oh man. Oh, I hope this works. That was not, I didn't mean to say unique. This means there exists unique. I don't think that is the case necessarily. And it's not even needed, so let's get rid of that. Sorry, I think that was in the scan I made yesterday. All right. Anyway, going on here. Where was I? So since F is surjective, I can find a point that maps to Q, and then I can find a chart there. Smoothness of G gives me local coordinate representative is smooth, and let's see here. So I can then look at the local coordinate representative of the composite. Kind of the same calculation as before. It's the composite of the local coordinate representatives of G and F, both of which were given to be smooth. Consequently, the composite smooth. In the reverse direction, pretty much very similar calculation. G composed of F is the local because of what we just worked out. The coordinate representative G composed of F is coordinate representative G composed of coordinate representative of F. But since F is invertible, F hat is invertible rather, not F. It's just the local coordinate representative F, which is invertible. That's what local diffeomorphism gives us in part. Then we can solve for G hat by composition of F hat inverse on the right. So on the previous part, it was composition of F hat inverse on the left. Now it's on the right. So that's why A and B are different. They are different. But they're also very much the same. Okay, moving on here. Problem 29. This problem. So let's see here. What can I say? So we're supposed to show that complex projective space is defined in problem 1.9 gives us a smooth submersion from non-zero n+1 complex vectors to complex n projective space, and also that CP1 is diffeomorphic to S2. However, we're not going to do part B because we already did part B. That was problem 6 on mission 1, which was rather difficult. Now there may be a way to prove part B from part A, and in fact I think I need to think more about this problem. This is actually an important diffeomorphism. We should understand more concretely as it relates to stereographic projections and so forth. This shouldn't remain mysterious to us. I've read some solutions online, and there's something more to learn here. This is actually a very popular qualifying or homework question in the sphere of online manifold theory from what I've seen, leafing through other people's problem sets. This is actually a very popular problem. Anyway, the smoothness of the projection here just amounts to looking at the local coordinate representative with respect to the homogeneous coordinate map, and it's just this maps to that, which is smooth. Assuming we're in the VK domain for VK, which is just to say that ZK is non-zero, and since k is arbitrary, and so you can do this for every VK, which then of course gives you an atlas, And so we've shown that the local coordinate representatives of pi are smooth for all charts in an atlas, therefore pi is smooth. And so we want to show it's a submersion. That's a little bit trickier. And I have pages and pages I've written for this, but here's what I got for you. So my choice was to just explicitly provide curves which map to the basis for CP, which map to, let's see here, how many? I believe 2n linearly independent vectors in CPN. So if I can do that, that shows that pi is a submersion because CPN is a 2n real dimensional space, if I recall correctly. Now, so what I do is I just map, I look at these coordinate curves, and part of the nuisance here is that, you know, we're kind of in between worlds. We have a complex example, but we haven't quite done the legwork to do the complex notation faithfully. So I'm a little bit apprehensive to just full bore do complex multivariable complex stuff in here, but I have a strong suspicion that if you did, some of the things would actually collapse down and this would be much simpler. I haven't had the, what's the word, headspace to do it at the moment. Definitely on my list of things to do is to come to a fully multivariate complex understanding of this example. I think that would be a vast improvement on what I have here. But anyway, here it is. So these coordinate, these are curves, these are other curves, alpha sub j, beta sub j. I can do one for each j, and each j not equal to k, of course, because I'm working for the z naught and vk, which have the you know, the kth component of z naught non-zero, and as such, these really are curves in that in the inverse image of the vk, which is what I called uk. Anyway, so clearly the derivative at 0 is ej, or iej, and that corresponds in Cn plus 1 to be either the derivative of the jth coordinate in the real sense, or the jth coordinate in the imaginary part of the jth coordinate. So here we have zj is xj plus iyj. So that's the, you know, the real and the imaginary components, coordinate functions to the complex jth coordinate. And that's our standard identification of Cn plus 1 as a 2n plus 2 dimensional real space. And so, you know, I'm not doing this for j equals to k, but for everything else I'm doing it, so that means there's 2n of these here. And, but of course the differential of pi acting on the velocity vector is exactly this. That's how we can calculate the differential using the curve calculus. The calculus of paths, rather, I suppose. And so if I actually look at the composition of pi composed with alpha j explicitly, I get this. If I look at the composition of pi composed with beta j explicitly, I get that. Maybe you can't see it. Sorry, I don't know where I am. Yeah. So when I look at the composite of pi with alpha j, I get this, which gives me that. And when I take phi k of that, I just get 0, 0, 0, t, 0, 0, 0. T over 1, see, because there's 1 in the kth entry, so that's what this sorts out to, which means that when I differentiate it, I just get a 1 in one spot. And, you know, likewise, when I do it for the jth one, I get an I in that one particular spot. And I'm being a little bit fuzzy. I didn't really want to count because, like, the counting is a little bit troublesome because it depends on whether j comes before or after k to the precise spot that 1 or the I goes in. Just rest assured that as j goes through all the values not equal to k, we definitely hit every single one of these entries. You know, we hit every single one of these n entries, all right, and with 1s or with i's. And as such, that's 2n real linearly independent vectors, which means that we've shown that at least for the point in vk, that the differential of the pi is onto the tangent space of complex projective n space. Yay. So that means it's a smooth map with a you know, a differential which is onto, therefore it's a submersion. All right, and again, as I've told you guys, I have a suspicion that Part B follows from Part A, but I currently have a mental block, so I'm just going to leave it. Now, problem 30, we have the map phi from R4 to R2 defined by such. We're supposed to show that 0, 1 is a regular value, and that the level set inverse image of 0, 1 is diffeomorphic to S2. So, all right, I calculate the Jacobian of this thing with respect to the coordinates. I get that. In order for the rank of this to be 2, we need the rank of this to be 2 for it to be a surjection. And let's see here. Yeah. So the question then is, what is the inverse image of 0, 1? That's the Jacobian. I just need that to be rank 2 for the points that are in this set, all right? So to put phi inverse of 0, 1 means that we've got x squared plus y equals to 0, and the sum of x squared plus y squared plus s squared plus t squared plus y equal to 1. But if we make a substitution, I think we get at y squared plus s squared plus t squared equals to 1, right? And anyway, the larger point here is for this 4 tuple in the inverse image, we cannot have y, s, and t all be 0. And if we look at the determinant of it, so like one way to check rank 2 is to check the determinants of like all the 2 by 2 submatrices, which give me this, that, and that. And if it's the case that x, y, and s and t are not all simultaneously 0, then clearly this is non-zero and that is non-zero. It just takes one of these non-zero and we've got rank 2. So anyway, I sorted through the cases here, and we can see that, every point in the inverse image of 0, 1 is in fact a regular value. We have rank 2 for the Jacobian, and hence rank 2 for the differential. All right. The diffeomorphism, what do I have to say about that? I'm not sure I have much to say. Let's see here. Yeah, I don't quite see how to prove the diffeomorphism explicitly. I mean, I see evidence of it, but I don't have a solution there. Sorry, guys. Maybe you found one. I mean, it may just be as simple as I told one of you guys to start with. I just talked myself out of that. I feel like there's a hole in that. All right, problem 31. We have an embedded m-dimensional submanifold. We're supposed to talk about the unit tangent bundle. So I got a lot of writing here, but basically all I'm saying is that you can define coordinates on the tangent bundle by, let's say, xv. Phi of xv is just list the coordinates of x, list the coordinates of v. That's the coordinate map on the tangent bundle to Rm. And so if we look at we can define the unit tangent bundle to actually be the inverse image of 0, 1 under the map that I defined right here. F of xv is v dot v, right? So then f inverse of 0, 1 gives me the set of all xv such that v dot v is 1. Now that's not M, that would be the unit tangent bundle of all of Rn. But if we restrict that so x is just taken from the submanifold, then we definitely have UM. But the thing is, we have theorems about restricting smooth maps to submanifolds, so I might as well just work on all of Rn. And so that's what I did. I worked on all of Rn, so my f of xy is this. Calculated Jacobian, it's that. So basically, again, G is f restricted to M. G is f restricted to Tm, rather. And so I have the rank of dg to be 1 because these can't all be 0. So there's at least one of them non-zero. Therefore, it's rank 1, which means that Um is an embedded submanifold of codimension 1 of Tm, but since Tm has dimension 2m, there you go. All right. I don't have too much to say about that one. That one's pretty relatively straightforward use of the Oh, the regular value theorem, I guess it was called. Let me look that up for a second here. As you can see, my book is lacking its cover. That happens to these a lot of times. The rest of the binding's pretty good, though. Let's see here. Maybe it was chapter 5. Where's that thing? Where'd you go? Show yourself. Yeah, more or less this theorem. We're using this theorem. I've used this theorem. Maybe I haven't said I'm using this theorem, but this theorem right here. Every regular level set of a smooth map between smooth manifolds is a properly embedded submanifold whose codimension is equal to the dimension of the codomain. So basically that's a formalization of the thing I often say, which is like if we've got, k independent equations in an n-dimensional context, then we get an n minus k dimensional set. That formalizes like the degree of freedom counting that I like to do sometimes to try to understand the dimension of spaces. Now this brings us to problem 32. We've got this lovely function here. And the question is, which level sets of F are embedded submanifolds of R2? For each level set, prove it's either that it is or is not an embedded submanifold. All right, so calculate the Jacobian. In this case, it's just a row 1 by 2 matrix. So for this to be less than regular, for this to be not be a regular point, I would need both this and that are 0. Right? If either one of those is non-zero, then it's a regular point, and consequently, the inverse image of such points would be a curve, a smooth curve, I suppose. Codimension 1 and R2, right? Now, so that's this and that. There are 2 points. You either get 0, 0 or minus 1/3, minus 1/3. Every point except for those 2 points is regular for F. And in particular, we can figure out as well what those levels are. So like 0, 0 is on the level 0 curve, and minus 1, minus 1/3 is on the level 1/27 curve for F. So if C is the inverse image of alpha, where alpha is not equal to 0 or 1/27th, then we can be confident in knowing that every point in C is regular for F, hence C is an embedded submanifold by the regular level set theorem. Which is to say it's a smooth curve in this context. All right. Do I have it all? Yeah. All right. Great. Now, this next one's kind of interesting. So again, kind of the same kind of song and dance here. You've got this set MA, which is defined in this way, and the question is, which values of A is an embedded submanifold? And I don't think I've really answered the second sentence, so I'll just leave that. So here is the formula, which I multiplied out because I thought that might be helpful. I calculate the derivatives. So in order to have a critical point, we need both that and that is 0. So in particular, we need y is equal to 0 at critical points. So that means that y is equal to 0 and x must be a solution to this quadratic equation. But actually going back to the beginning, if y is equal to 0, if x is y in MA, and y is equal to 0, well that pins things down quite a bit actually, because that means either x is 0, 1, or A. In other words, those are the points in MA which lie on the x-axis, and so we should find if partial x is 0 at any of these points. So that can only happen if A is either 0 or a half or 1. So for these 3 values of A, we have, is an embedded submanifold? Hold on a second here. Oh, I've got a not equals here. For A not equal to that, it's an embedded submanifold, right? Because for A equals to this, it's likely not an embedded submanifold. All right. And again, I'm not proving that for A equals to 0 and 1/2 and 1, it is absolutely not an embedded submanifold. I'm just content to use the positive application of the regular set theorem. Because you could, well, anyway. Ooh, this problem. Ah, it's beautiful. Problem 34 I made up, which means I took it from a book I knew where the solution was. So show SLNR, which is determinant 1 matrices, is a properly embedded submanifold of n by n matrices. Now, the solution I show you here is example 2.5.5 in Conlon's differential manifolds book, which I have sitting over here. This is Berkhaus, or Advanced Text, Lawrence, Conlon, Differential Manifolds, 2nd edition. This is a good book. I think this is a good book to read after the course. It's a great second book in manifold theory. If you're really well prepared student, like if you've had like a couple semesters in analysis and a topology course, and you are well versed in reading mathematics, this is a good first book. But this is a very good book. But it goes fast. And I had a good student have trouble kind of following it, even though he was a very good student. But it has its place. Anyway. Certainly the book we're using is a little bit slower paced and a little bit more, well, I don't know, like Conlon's got a lot of details too, so I'll shut up. But here, for example, we have the determinant is a polynomial in the standard coordinates, right? There's the formula for it. So the determinant is a smooth map, and we just need to show that it has constant rank 1. If we can show that, then that would suffice to prove that SLNR is an embedded submanifold of dimension n squared minus 1. All right, if we can show that every point on the inverse image of 1 for the determinant is a regular value for this map, then we're good by the regular set theorem. Now, so we need to show the determinant has constant rank 1, that map. All right, so that means that we need to calculate the differential of the determinant. So here's what he does. He seeks a curve to invertible matrices with gamma of 0 being A and gamma of t being in GLN for t sufficiently small. Now the way he does that is a little sneaky. He lets gamma of t be equal to 1 plus t in the first row of A. All right, and then just leaves the rest of the rows of A alone. Now, of course, gamma of 0 is A, which is in GLN by assumption. And since GLN is open, it must be that gamma of t is still in GLN for t sufficiently small, because you can't jump from the determinant being non-zero to the determinant being 0 infinitesimally. There has to be a range of time it takes for it to get from invertible to non-invertible. And certainly gamma of 0 is invertible, so we can't jump straight to non-invertible. For a sufficiently small time, it doesn't happen by the continuity of the determinant. So, great. And on the other hand, the determinant of this curve is 1 plus t times the determinant of A using the multilinearity of the determinant, and that's non-zero for epsilon sufficiently small. But the derivative of the determinant of A acting on gamma prime of 0 is that, which is determinant A. Therefore, the rank the differential of the determinant is 1 for A and GLN, and then we get that SLNR is a, So this is interesting, actually, now that I'm reading this. See, because I've solved problems after this, which essentially deal with the same mathematics here. So the way this is dealt with in Lee is his problem 7.4, as we'll see in the solution, I think, to mission 4. But this is clever, and I was going to show this to you guys in class, and it just never happened, and I'm sorry that didn't happen, because it would have been helpful, but anyway, so this is another kind of sneaky trick to get matrices close to a given matrix, exploiting the continuity of the determinant, so, and also the fact that GLN is open. But, all right, so that's that for this one. Move on to mission 4 next.